Hi everyone! Today we're going to look at our next lesson of axioms of equality. First thing I want you to do is pause the video and just try the 3 opening exercises quickly. So just pause, try them out, and then check your work in a moment. Okay, if you're back, when we're looking at the opening exercises, the first one shows us that we have an angle, JKL, with an angle bisector KN. Now, it's hard to kind of see that without drawing yourself a picture. So I would draw an angle. We're going to label it JKL. And we also have the angle bisector KN that's going to come through. Now, the angle JKN is going to be 2x plus 15. And we know the entire angle adds up to 86 degrees. We want to determine the value for x. So when we try to find x, we need to know one of our vocab words to help us here. When we look at that angle bisector, that means that these two angles are equivalent to each other. So we can have 2x plus 15 as this angle as well. Now, when we go to solve for this, we should know that the two smaller angles add up to the whole angle. So we're going to solve for x by taking 2x plus 15 plus 2x plus 15 equals 86. Okay. When we combine like terms, we end up with 4x plus 30 still equal to 86. We can subtract the 30 from both sides. We'll have 4x equal to 56. And when we divide by 4, x equals 14. Okay. So that's our first one. The second one is another throwback for us where we're looking at line segment MN is 5. So from here to here. NO is 7, while the entire thing is 12. We want to know if it's collinear. Now remember, collinear means 3 or more points that are all falling on the same line. And an X is why or why not, and to explain. The answer in this case was yes. Our reason why is because 5 plus 7 does equal 12. So our two segments are MN plus NO do add up to the whole thing MO, so we know it's a straight line. Last opening exercise we're looking at here, we have given the points A, B, C, and D are collinear. We know here that AC, this entire thing, is congruent to DB, this entire piece, and we want to explain why the smaller pieces, AB and CD, are congruent. If we look at this, we know they're congruent because we're already told, just like yesterday, we're told a given that we know for sure that those pieces are congruent. If that whole thing's congruent, they both overlap at one place. So they both share BC. Okay, this is BC here. If we remove BC from both sides, if we take that out, we're left with AB and CD. So if we're taking an equal portion from both pieces, the remaining pieces have to be equal. So if we remove BC from both AC and BD, then we'll still have two congruent pieces of AB being congruent to CD. Okay? So those were things that we've seen before in the past. We're just explaining and justifying. But today we're going to go into axioms of equality. Those are geometric properties regarding length and angle measure that are used to justify arguments or geometric proofs. Anytime you want to back something up, it's just using some kind of logic. Basically, an axiom is just saying something that we probably already know, but we're just going to give it a special title so we can use it when we're justifying along the way. Each of these opening exercises use one of these axioms. We're going to talk about it. The axiom that we learned about so far is that the parts add up to the whole. Okay, so each individual piece, like if we look back here, the two smaller angles added up to the whole thing, 86. The two smaller segments added up to the whole segment, MO, and same thing even in C. So we're going to try to use that piece and kind of look at what we're given. So yesterday we talked about explaining everything and just giving the backup and giving the reasoning with it. Here we're just going to write it out with specific reasons after each piece. So we're going to organize our ideas with this table. So our first reason always, it just matches exactly what we're given. So that always should be your first reason, is just to recap what we have here. Those two equal portions. So I'm even going to mark them that I have CE and EF and EB equal to ED. Remember, we can use equal as long as the line segment on top symbol isn't there, but we'll go with it for this one. Now, if we look at the next piece, it's adding CE and BED and FE and ED. This property is just known as the addition property. Nothing fancy. It's just adding our pieces together. And finally, if we look now, so if we added those two smaller pieces, so if I look, I took these pieces, CE and EB, and if I look at FE and ED and add those smaller pieces, I'm adding them, but they're going to still equal CB to FD because the parts add up to the whole. Going on to the next page here, we also have the subtraction axiom. So we just saw the addition axiom. You could call it axiom, you could call it property. I usually use property. Either way is fine. Now, similar with angles, as long as the measure is indicated, that little M in front, we can use the equal symbol. But if it's not there, we stick to congruent. So for this one, we're just going to stick with our equal symbol. Now, given that BAD, so this whole angle, BAD, is congruent to the angle CAE. So that's what they stretch upon. We want to prove the smaller angles are equivalent. Why would this have to be true? So it says to come up with some angle measures. Let's just say that angle BAD equal to 50 degrees. That would mean angle CAE would also be 50 degrees. Now, if I wanted to find the smaller angle in here, we could give maybe this angle some number. Let's say it was 30 degrees. If I subtract both of them by 30, there's no way I would get a different answer. They would both equal 20 degrees. So we know this would be true. And it's kind of like the property we saw back from the opening exercise. So let's try to put it all together. So again, whatever we start with is known as our given. It's exactly what was told to us when we started this statement and reason table. If we had BAC and CAD equal to CAD and DAE, it's because the parts add up to the whole. Those two smaller angles make up the big purple angles that are indicated. So again, the parts add to the whole. So the parts add up to the whole. Now, notice, this is our big property here. It's equal to itself, just like the 30 degrees. We subtracted the same amount from both. If we subtract the same amount from both, that's known as the reflexive property. That's going to be one of our most popular properties throughout this unit. It's just whenever you use something that's equal to itself. So we're taking the same thing away from both. So we know it's taking the same amount. And if we take that same away out, just like we saw in part A, we got 20 degrees for both, it's going to be known as the subtraction property because we're subtracting out here. Notice we went from the measure of the angles here and we subtracted CA from both. So it's like we eliminated CA from both of them. So we canceled them out by subtraction and we're left with just the two angles that we wanted in the given. Okay, and we can go ahead and fill in the reflexive property. Can be used when the same angle or segment is congruent to itself. Every situation, that's what it's going to boil down to. Now, our last one for today is talking about the substitution axiom, where we can take quantities that are equal to each other and just substitute them in, like plugging in. Like when we solve for x, we plug that in. Now, if we want to organize our ideas the same way we've been doing, we have this table. So we're going to write that given in. So what I want you to do is write exactly what the given says. So this whole thing should be what we write down here. So lines M and N intersect to form angles 1, 2, 3, and 4. Now, our next idea is just to prove why vertical angles are congruent. It's something we already know, but we're just kind of going to find some backup. We're going to prove it. That's our goal here. So that should be the last step of our proof when we're done. Now, as I'm going through, I need to think of anything I might know. So something that I know is that angle 1 and angle 2 equal 180 degrees. I know that because angles on a line add to 180 degrees. So remember, we're just writing down why we know something, what we can say, and we're just trying to back up our information. So with that same idea in mind, we know that 2 and 3 also would be along a straight line equaling 180 degrees. And I can just write R2 here. So reason 2, so I don't have to write it down. I can write same as, I put an arrow, anything I'd like. Now, what I want to look at next is they both are equal to 180 degrees. That essentially means they are both equal to each other. So angle 1 plus angle 2 is equal to angle 2 plus angle 3. That's our new property. That's the substitution. Anything that equals itself can be set equal to each other as well. So if they both equal 180 degrees, we can set them equal to each other. Now that we know they're both equal to each other, one thing we should realize is that they both have this angle too. And I just put the congruent symbol in there. If you set with equals for this one, that's okay. So I see this angle 2 and angle 2. Remember, that is our reflexive property from before. Anything equal to itself is the reflexive property. And since if we look at this now, 1 plus 2 and 2 plus 3, 2 and 2, we can cancel out those 2's and write angle 1 is congruent to angle 3. And our reason to be canceling something out is subtraction. And you'll notice, I know I'm done because I was able to figure out how to get that as my last statement down the left side, Okay. So these have just been an overview of how we look at these many proofs, if you will, trying to prove our thought process and kind of go with it. Tomorrow we're going to practice this more, but I hope you enjoyed your video.